In this video, I'm going to show you how to solve problems in vector diagrams. So in this problem, we've got a diagram below here. The diagram has a triangle PQR and two of the sides are labeled. Side PQ is labeled as vector B here, and then side PR is labeled as vector C. And we want to express this other side, QR, in terms of the vectors B and C. Now, first of all, let's talk a bit about how these vectors are labeled. Usually we see the arrows here at the ends of vectors, but here we see the arrows in the middle of the vectors. This middle arrow notation is convenient when we have multiple vectors ending at the same point, such as PR and QR. They're both ending at R. If we put the arrows at the end of the vectors, then there would be two arrows that are right on point R, and it would be kind of confusing because the arrows would collide. But it's a lot easier to see when we put the vectors in the middle. It makes it a lot more clear because the arrows aren't colliding, and we can tell which way the vectors are going very easily. Alright, so how are we going to express QR in terms of the vectors B and C? Well, why don't we start with the triangle law for vector addition. The triangle law just tells us that we can add vectors end to end. So say we have vector PQ, that's this vector right here, and say we add the vector QR. So that's like traveling from P to Q here, that's vector PQ, and then from Q to R, that's the vector QR. And another way to say that is just starting at P and ending at R. So that's equal to the vector PR. And now we can fill in with what we're given. We're given that PQ is B, so PQ becomes B, vector B. And then we're also given that PR, that vector, is vector C. So we'll fill in C for vector PR. And then we want to find QR. That's the thing that we're looking for. And that's right here, QR. Put in our operations. B plus QR is equal to C, and now we can just solve for QR. So go ahead and subtract B from both sides, and then we just have that QR is equal to vector C minus vector B. And there we go. We've got QR in terms of B and C. There is our final result. Alright, here's another problem for us to do. So we've got another diagram here, and this diagram consists of two triangles. We've got a small triangle XYZ that is contained within this bigger triangle XWZ. Alright, and we know that XW is A, that's labeled as vector A, then XY is labeled as vector B, then ZY is labeled as vector C. Now we want to express these vectors xz and wz in terms of our given sides here at A, B, and C. So why don't we look at xz first? That's this vector here for the side going from x to z. And hey, look, that is part of a triangle where we know two of the other sides as their vectors B and C here. And that's kind of the same setup as was in the previous problem. In the previous problem, we knew two sides of the triangle, and then we were trying to find out the third side. So why don't we do the same thing here? We'll use the triangle law for vector addition, and we'll just say we want to find the vector xz. So why don't we express that in terms of the other sides of the triangle? So going from x to z is the same as going from x to y and then y to z. So let's write that down. xz equals xy vector plus yz vector. And now let's substitute in for what we know. So we know that xy, that vector, is equal to vector b. So we can just write down vector b over here. And then how about yz? Well, we know that zy is c, so now we have to reverse it. We just want the vector c going in the opposite direction from y to z. And the way we can get that is we can write negative vector c. Alright, so let's go ahead and put our operation between b plus negative of the vector c, and that is going to be equal to xz. So we're pretty much there. We have xz in terms of b and c, and let's just clean that up a bit. So xz is equal to vector b minus vector c. And there we go, we've got xz. Great, so we're about halfway there. Now we just have to solve for the other vector, wz, in terms of vectors a, b, and c. Now before we solve for wz, let's go ahead and label xz in our diagram with what we know it's equal to. So xz here, let's make a little arrow for x going to z. That vector is equal to vector b minus vector c. And now it's easy to tell that in the large triangle here, we know two of the sides as they're labeled vectors in terms of a, b, and c, and we're looking for the side wz. So we can do a similar thing here. We know two of the sides. We're looking for what is the third side. So let's just use the triangle law again. So let's write wz, that's the vector that we want to find, and that's equal to, well, we can just go from w to x and then x to z. So that's equal to the vector wx plus the vector xz. Now let's go ahead and sub in our given information into this equation. So first of all, wx. What is wx? Well, we know that xw is a. So we want wx, we just want to flip that around, have it go the opposite direction, so we can just tack on a negative in front. So wx, that'll be negative a. Okay, and then how about xz? Well, xz, we already have that. That's what we found in the previous step. That's just vector b minus vector c. So negative a plus b, and then minus c. And there we go. That is what wz is. Perfect. So now we've got wz in terms of vectors a, b, and c, and we've also got vector xz solved in terms of the given vectors as well. So we're done. All right, here is a final problem. So in the parallelogram below, which of the following equals the zero vector? Okay, so we've got this parallelogram a, b, c, d with a point O in the middle of it, and its diagonals go through the point O, and we've got four choices for various expressions of vectors, and we want to figure out which of these choices evaluates to the zero vector. Alright, so why don't we start with the first choice first, vector AB plus vector BD. Well, that's just part of a triangle law for vector addition. Vector AB is from A to B, and then vector BD is from B to D. So if we go from A to B and B to D, then really we're just going from A to D. So that's equal to the vector AD. But is AD the zero vector? Definitely not. That goes from point A to point D, and those are two different points. So no, it's not number one. That's not equal to the zero vector. Now let's go on to the second choice, vector AB plus vector BO plus vector AO. Just looking at the first two vectors here, AB plus BO, that's kind of like the previous choice. This is just another triangle law thing. So vector AB runs from A to B, then vector BO runs from B to O. So from A to B and from B to O, that's the same as going just from A to O. So these two vectors, when we add them together, that just gives us vector AO. Alright, and then vector AO plus vector AO, well, that's just going to be 2 vector AO. But AO definitely is not the zero vector. That goes from point A to O, 2 different points. That vector has a non-zero length. So nope, 2AO is not the zero vector. Alright, let's look at the third choice here. It's vector AB minus vector CD. Now it doesn't look like these vectors have any points in common. Previously, we were able to use the triangle law for vector addition because vectors had points in common. AB plus BD, that had a point B in common here, and AB plus BO, that had a point B in common there as well. But B and C, those are not common points. So what do we do here? One thing to notice is that we're told that this diagram is a parallelogram. So that means that the sides of the parallelogram, pairs of opposite sides here, are congruent and parallel. So in particular, we have that the side AB is congruent and parallel to the side DC. So let's write that in terms of vectors. So the vectors AB going from A to B and DC going from D to C, these have to be the same vector because they have the same direction. From A to B is parallel to from D to C, and they have the same magnitude. So yeah, they're the same vector. So let's write that. Why don't we write it over here? Vector AB, this vector, is congruent to vector DC. Alright, so now let's use this bit of information. If vector AB is equal to vector DC, then we can just substitute that in right here for AB. So AB minus CD is equal to DC minus CD. Now notice that negative vector CD, the negative just flips the direction, so negative CD is equal to DC. So this is really the same as DC plus vector DC, which comes out to 2 times the vector DC, and vector DC is not the 0 vector, so twice of it is not the 0 vector. So it's not choice 3 either. Okay, so it's got to be choice 4, right? Maybe it's a trick question. Maybe none of these are the 0 vector. So we better work out this choice just to make sure. Alright, so AB plus CD. Well, why don't we use the same equation that we used earlier, AB equals DC. We used that in the previous choice to simplify it, and this is very similar, so let's use it here also. So subbing in for AB, we have that AB equals DC, so this becomes DC plus CD. Okay, and so we know that the vector CD is just negative of the vector DC if we flip the direction, so DC minus DC is what that simplifies to, and DC minus DC is just 0. Yeah, that's the 0 vector. So this choice, this is it. This is the 0 vector. You can also see that from the triangle law for vector addition, DC plus CD, that's like saying go from D to C and then go from C to D. So really go from D to D, you're not moving at all. So that is also the 0 vector. You can see it that way too. Either way, you see that it's the 0 vector. And so that's our answer. That's the 0 vector. Great, so now we're getting comfortable with manipulating vectors through addition and subtraction. And in the future, we'll also learn about rescaling vectors and taking linear combinations of vectors.